Good evening, everybody. So this is Wei. Let's take a look at the second lab. So the second lab, the topic is sampling distributions and central limit theorem. So last Friday we just talked about what is sampling distribution. So let's take a look and see the definition again. So sampling distribution is the sampling distribution of a statistics. So in the most frequently used example in this class, we talk about the mean. Okay, for example, the sampling distribution of the mean income. It's the distribution of values taken by the statistic in all possible samples of same size from the sample population. So the whole idea is the population is too big. What we do is we take a sample. But imagine if you can take more than one sample, you take multiple samples. And for each sample, you can compute the statistics. For example, the mean. Then you would get multiple sample mean. And these multiple sample means, they would look similar, but not exactly the same. And you can visualize them just like a histogram or something. And then the shape of the histogram, the distribution, that's what we're talking about here, the sampling distribution. And we mainly talked about two kinds. The first kind, it's the sampling distribution of proportion. And we're saying that, if you take a look at the formula sheet, we're saying for the sampling distribution for the proportion, these are the formulas for the mean and the standard deviation. And we're saying that if you have a large sample size means these two conditions satisfied, NP bigger than 10 and n times 1 minus p bigger than 10. We're saying the sampling distribution of p hat follows a normal distribution with this mean and this standard deviation. Similarly, for the sampling distribution for mean, this is the mu and the sigma, and you can see for the standard deviation, the standard deviation is kind of similar. You have the standard deviation divided by square root of n, which again tells you that if n increases, the standard deviation decreases. And we're saying that there's a theorem called central limit theorem, which basically says if y follows, doesn't matter y follows any distribution, so it doesn't matter what's the population distribution, as long as the sample size is bigger than 30, we have the sample mean approximately follows a normal distribution with mu and sigma over square root of n. So as I mentioned, the central limit theorem is one of the most important, not one of the most important theorem in statistics. And you can explain this by using this picture. So basically assume you have any kind of population distribution, but if your n is larger than the x bar, the sample distribution would always follow a nice normal distribution, okay? And then we're going to use this lab to show you a real example of how we do this, okay? So so let's take a look at the settings of the lab. It's called how many flaws in a glass sheet on average. So it's kind of like a quality control process in industry. So it says quality control process in the glass manufacturing industry is very important because you don't want the glass coming out of the factory has too many flaws. So you want to reduce the, you want to increase the perfect rate or failure rate reduce. So to determine the causes of flaws before a large number of flawed glass is obtained allows saving time and money. So here it says a quality inspector at a glass manufacturing company inspects sheets of glass to check for any light imperfections, and one sheet, a box usually contains 6 or 35 sheets. So how does the number of flaws vary from sheet to sheet? Like on average, how many flaws are you expecting from one sheet? From one box containing 6 sheets or one box containing 35 sheets. And how does the distribution look like? Some box might have 1, some box might have 0, some box might have 2. So what's the distribution of the number of flaws? Okay. So for this data, for this lab, we're using a simulated data. So it's not the real data, so we simulate the data using some distribution. But if you know this area a little bit, here we are using a distribution called Poisson distribution to stimulate this kind of scenario. And this is a very good approximation because in manufacturing, the number of flaws actually do follow Poisson distribution a lot of times, and so that's why we used this distribution here. Okay, so what's Poisson distribution? It's just like normal distribution. It's just another distribution, and later we'll see how it looks like. So we're going to assume that the number of flaws in a randomly selected glass sheet follows a Poisson distribution with parameter lambda equals 0.7. So for the normal distribution, we have two parameters. One is the mu, one is the sigma. But for Poisson distribution, we only have one, which is the lambda. Okay. So Poisson distribution is a discrete probability distribution specified by a single parameter lambda, and lambda has to be positive. In this case, we're going to use lambda to be 0.7. And for Poisson distribution, it's very special is that the mean is lambda and variance is also lambda. So for example, if we're using the Poisson with 0.7 to stimulate this scenario, we are assuming that in average there are 0.7 number of flaws per glass sheet, per randomly selected glass sheet, and the variance is also 0.7. Okay. So how does Poisson distribution look like? So here if you're using the calculator tools under the stats menu, you can visualize it. Okay, so let's go to, again, my data is very similar to yours, but maybe slightly different. Okay, so let's go to data and then simulate. Then there are all kinds of distribution. You can play it by yourself to see how they look like. So we are using Poisson here. So Poisson, oh no, we're not simulate, sorry. I am not feeling well. Okay, we are using statistics and then calculator, Poisson distribution. So this is the default mean equals 10, but we don't want 10. Let's go back. Mean equals to 0.7, and let's put smaller than 0 here. Okay, compute. So this is how Poisson with lambda equals to 0.7 looks like. So 1a asks you what's the shape of the distribution and how can you say about the typical number. So the shape is clearly heavily right skewed, right? Because we have the majority, almost 50% to be 0. 0 means no mistake, which is something people like to see because you don't want, usually you expect that most of your products contains 0 flaws, right? And then you have very small chance for a product to contain 4 flaws or 5 flaws, which is also quite realistic. So 1 flaws, or that's the maximum you can see usually. And it asks, what's the typical number of flaws? So typical means, here it would be the most likely number. So the most likely here is 0. So it's very likely that it doesn't contain any flaw. What's the probability that there are no flaws? So no flaws means the x here represents the number of flaws. No flaw means smaller than 0, which is the same as less than or equal to 0 here, because it cannot be negative. You cannot have negative amount of flaws. So in this case, it's about 49%. C says, so this is for one glass sheet, okay? And then C says contains boxes containing 6 glass sheets. So imagine you have x1 until to x6. So it asks what's the fraction of boxes with all 6 in perfect condition. So we know that the probability of one sheet contains no flaw, which equals to px equals to 0, equals to about 49.65%. and here ask if you have 6 of them, what's the probability that all of them contains no flaw? Okay, this, and you can assume independence. So this is a really good practice for the independent rules, and also how to calculate p. In this case would be, if I'm using a1 to represent no flaw for the first class, then we are looking for probability of a1 and a2, so the second is no flaw, and a3 and a4 and a5 and a6. See, something like this. So this is looking for like this, and you can. It's a good practice. I'll leave this for you. Okay. So now it starts the lab. It says, suppose that the inspector selects 50 random samples. Each consists 6 sheets, and then another contains 35. So we have two random samples. Two data sets. The first data set contains 50 samples, and each sample with sample size 6. The second data set also contains 50 samples, and each of them sample size is 35. Okay, and then these two data sets are stored in lab2a.txt and lab2b.txt. Okay, so so you don't have to simulate the data, and it's all provided, but I simulate new data, so it will be slightly different than yours. Okay, so if you take a look at the data, for example, lab2a, every column is a sample. So in this case, I have my first sample. If I move this to the left, my first sample contains 6 sheets of glasses. The first, and the number of flaws the 6 sheets contained are 0, 0, 0, 1, 2, 1 flaws. Okay. Similarly, you can, every single column is a sample, and I have 50 of them. Okay. So the first, we know that number of flaws follows a Poisson distribution, right? But what about the average? So the sampling distribution is about a statistic. In this case, if we focus on the mean as the statistic, what would happen? So to ask you to obtain the average number of flaws for each sample consisting of the 6 observations with the summary statistics, and save the results. So basically, we need to compute a mean, the average number of flaws for the first sample, for the second sample, for the third sample, until to the 50. So we'll get 50 sample means. Okay. So how do we compute the sample mean of each column? So let's go to statistics, since we are computing numbers, like number summary statistics, and then we're doing columns. Okay, hopefully I'm doing the right thing. Let's select all of them because we want to consider. So you can click on the first one and then hold on Shift and then until the 5th one. We only want the mean, because if you do all of them, you would have so many information, which we don't want, a really messy table now. And then here it says output, so check this store in data table, because if you don't click on this, it would just show you a really long table, which we don't like. We actually want to store the mean and then analyze it for the future. Okay, so let's do store in the data table to compute. And then, so as you can see, we have 2 new columns. The first column, it's the sample name. The second column, it's the mean, the average amount of flaws contained in each sample. And remember, in this case, the sample size is 6, okay? Sample size here, it's the number. We have 50 samples. Each sample contains 6 sheets, so sample size is 6. So we have the average now, and 2a asks us to get a relative frequency histogram. We already talked about how to make a histogram in lab 1, so hopefully you know how to do it. So okay, histogram, so we're going to graph, histogram, and then the mean, okay, and then type, it's relative frequency, starting at 0, as requested by the question, with 0.01, okay, and you should add a title, so relative histogram of the sample means is to compute. So this is how it looks like, okay? So to be asking what's the shape, does it be normal? I would say it's quite, it's quite close to, but not exactly, because still, see, it's quite still a little bit right skewed. We have this here, and you can video sort of like this. So it's slightly right skewed, I would say. And it asks you to compare this to the individual observation in question 1 in terms of center, spread, and degree of skewness. So if you go back, here, oh no, yes, okay. So on the bottom, I have the Poisson distribution. This is my parent distribution or my population distribution. And I simulate my data from this. So this is distribution of 1x. Okay, and it's really right skewed. And the center is almost 0, because I see maybe here 1, the center, or between 0 and 1. The mean is 0.7. Exactly, the mean is 0.7. Okay, so if you compare this with this one is definitely more normal. I can see it's less skewed, right? The center is roughly similar, because the center here is also maybe roughly 0.6, 0.7. Here the mean is also 0.7, so they are similar, I want to say. The spread, this one is definitely more concentrated, because I mean I have the majority between 0 to 1. The maximum is 1.5, right? So it's pretty concentrated, pretty dense. But if you look at the x, it's from 0 to 5, and a lot of them, there's like 2 is about, I don't know, 15%. So as you can see, this is not surprising, because here what we did, this is the distribution of x bar from sample size 6. So this is the average. So when you are taking an average, as we talked about, so in this case, we are dealing with sample mean, okay? And then the standard deviation is sigma over square root of n. So n is 6 here. So of course, standard deviation would be smaller. Standard deviation smaller means it's going to have less spread, okay? Okay, C says to get the mean, standard deviation, and standard error. What does the standard deviation measure? Compare the value to the standard deviation and the mean of, what does standard deviation measure? Compare the values with both the predicted mean and standard deviation. Okay. So here predicted is not really the correct word, but anyway, so what we are saying here is, Where was I? Oh yeah, the predicted, I would say expected would be a more accurate word. Why? Because based on this formula, based on these two formula, we know mu and sigma. So we know that the x follows, x is the amount, number of flaws in one sheet of glasses, okay? And then we simulated x from a Poisson distribution follows the Poisson distribution with lambda equals to 0.7. So this tells you that E of x mu, and use mu to represent, equals to 0.7. Okay, and also the variance is also 0.7. See, this is given by this sentence. For a Poisson distribution, the mean and variance are both lambda. So the sigma square equals to the variance, sigma 0.7. Okay, and so which gives us sigma equals square root 0.7, which equals to square root of 0.7 is 0.836, 0.8366, maybe 67, okay, roughly. Okay, and then based on this formula for sample mean, so now we want to know x bar, and so x bar in this case is the mean average number of flaws in a sample with 6 sheets of glasses. So n equals to, we know mean is the same, standard deviation becomes sigma over square root of n, which gives us, so if we're using x bar, sorry, I cannot type x bar, I'm just going to say this, x bar, this is the number of mean in a sample with 6. Okay, so we know that based on the formula, we know that the expectation of x bar equals to mu equals to 0.7. Okay, the standard deviation of x bar equal to sigma divided by square root of n, which is square 0.08367 divided by square root of 6. Okay, so we basically have this divided by square root 6, 0.3415. Okay, so that's what we expect. But how is this close to how is this close to the sample we have here? Okay, now let's compute it from the sample. No, what's this one? Okay, I need this one. Who's this one? Up to A. Okay. Okay, so we want a summary statistics about the mean and standard deviation of this column. So let's do statistics, summary statistics column. Let's do mean, and then let's just take all of them. You don't have to store them now. Actually, we just want mean. We want mean, variance, standard deviation, standard error. Is that all? Yeah. So based on this, I have mean is 0.696, that's very close to 0.7. The standard deviation is 0.30. Based on the formula, I have 0.34. That's pretty close, not too far. So yeah, that's question 2. Okay. And then question 3. Question 3 pretty much is question 3. So question 3 is very similar to question 2. Just instead of using the lab 2A, we can use lab 2B. And lab 2A has 50 samples, each one with sample size 6, and lab 2B has 50 samples, each one with sample size 35. So again, the first step is to compute the mean of each sample. So in order to do that, we are doing statistics, summary statistics columns, and then choose all the samples, and then choose only sample mean, and then store this in data table, compute. So we have these new columns, and we have the mean here. So the first one, 3A, asks you to do a relative histogram. So graph histogram, choose the mean, and then we're doing relative frequency, starting with 0, mean, and with 0.01, okay. And then put a title there. I'm just gonna ignore this for now. So this is what my histogram looks like, okay. And then 2B, 3B asks you about the shape. So the shape, I would say, again, because for histogram, it's very bumpy. It's not very smooth. I would say this one is quite symmetric. Like my center is kind of like 0.7 is right in the middle, and I have roughly similar amount of on the left and on the right. And it asks you to compare the center spread skewness with the histogram we had in 2A and then the one we had in the first question. So first, for the data, no, where is it? Statistics calculator Poisson with 0.7. So if you compare this one with the parent or the population distribution, this one is definitely more symmetric. The center is similar. It's here is 0.7. Center is also 0.7. And the spread, there's definitely less variation here because I mean my whole range is between 0 to 1, but here, as you can see, there is going to be possibility for 2 mistakes, 3 mistakes, and etc. And if you compare this to question 2, this one is more symmetric, I think, but you can do that. So 3 asks you to compute the mu, standard deviation, standard error, and compare this with the one in question 2, and then also compare this with the sampling distribution. So first, let's compute this. So statistics, summary statistics columns, and then you're doing the mean. Then let's choose sample size, mean, variance, standard deviation, standard error. Okay, so the mean again is very close to 0.7, and this is the standard deviation. So again, you should do the calculation for sample size n equals to 30. So basically now our x bar is the same, but you just change this 6 to 30 and compare your expected standard deviation to the actually observed one to see whether they're close or not. Okay, I'll let you do this part of work. That's 3. So 4, so what's our conclusion now? We definitely see that the sample mean for both data are more normal than the population distribution. And question 3, we increased the sample size from 6 to 35, and we see that the the data is more symmetric, and also if you look at the standard deviation, it's smaller, and the mean and the standard deviation is very close to the one we used if you use the formulas to compute it. Okay. And 4 says that in this part you will compare some probability derived from the theory from the observed frequency with the observed frequency in the data table now using, based on central limit theorem, the average number of flaws in a randomly selected is large enough. So for this question, lab 2B, we have sample size 35, which is bigger than 30, which we can, in this case, we can use a normal distribution to approximate the sampling distribution of X bar. So 4A says count the number of boxes of 6 sheets with all 6 sheets in perfect condition. Compare the corresponding relative frequency with the probability obtained in 1C. So in 1C, we had this, we're saying if you put 0 here, saying the probability of having no flaw is about 49.65%, and then it asks you to verify this. Compare the number. Oh no, for 1C you have to do the calculation. You have to use the independent law and then calculate the probability. Compare the number to the number of 6 sheets. So 6 sheets, that's number of boxes of, that's 2A. Where's my data set in 2A? Okay. So it asks you to calculate how many of them has all 0. All 0 basically means the average have to be 0, right? So let's do the average. Sorry, I didn't save it. The average. The column 1 to 50. We're doing the mean. If we order by the mean, oh, I have no sample with all 6 perfect. See, so mine probably is 0 for my data. Your data may be different because this is all my sample, and all of them contain some error. None of them has mean 0. Okay. 4B says assume the number of flaws is randomly selected by Poisson and blah blah. What is the probability that the average number of flaws 35? This is a good practice for the sample mean calculation. For the mean-based sampling distribution calculation. So basically, you're using normal to approximate the sampling distribution with mean mu 0.7 and sigma being this sigma over square root of 35, and then it's a z-score question because we are looking for probability of x bar is larger or equal to 0.9. Again, you do the calculation theoretically, and then you compare this but here I can show you how to use StatCrunch to do the z-score question. So let's go back to here. Statistics calculator. We're using normal, right? Normal, the mean is 0.7. standard deviation is what? Square root of 0.7. That's for one sheet. You have to do this divided by square root of n, square root of 35, which is 0.1414. 0.1414. Probability of larger than 0.9, which is about 7%. See, this is so much easier than hand calculation, right? Okay, and then it asks you to compare this with the real data. Okay, so the real data, the mean, we can order the mean, order this ascending. Okay, so larger than 0.9, I have how many sample? Sample 33, 1, 2, 3, 4, 5. 5 sample. So in that case, I have so from the data, I have 5 sample out of 35, which is roughly 1 over 7.14%. 14%. Okay. And based on the theoretical calculation, this is 8%, almost 7.8%. 7.8% from the Z table. Okay, I mean it's quite a big gap here, see, but the gap will be closer and closer if you have more samples. So here we have, I think the sample size is good now, but we need more samples in order, because if you look at the histogram, this is let me show you why this is happening. This is the histogram, this is the normal plot. We're basically using this curve to approximate this histogram. And as you can see, this one is still very bumpy, and then it's quite discrete, like it's not continuous enough. But if you have more sample, this will be continuous enough to this one, and you can approximate and you can calculate the area similarly. Okay. Or you can also use this histogram, so over 0.9, right? So I have 2 here, and I have 3 here, so 5. Okay. Okay, that is everything. Oh, this is very tiring. Okay, yeah, so this one I wouldn't say it's just, I understand that sampling distribution is something kind of hard and abstract to understand. And this one doesn't really have much background because we simulated data and there was a lot of statistics involved, kind of. So, but yeah, after you kind of understand what we're doing, and shouldn't be too bad. Okay. Okay. So, bye.